In this video, we're going to learn how those rolling 6-digit codes from your bank app actually work. And we're going to take a look at a tiny implementation of a time-based one-time password generator written in Python. If you've ever used 2FA, you've seen those 6-digit numbers in action and you probably used TOTP. Have you ever wondered how can your phone and the CIA server agree on the same secret code at the exact same time? We're going to look at a Python script from a repository called minOTP, which implements a full TOTP code generator in just a few lines. Here is the entire code example. Crazy, right? I guess the best way to start looking at it is from the entry point. If you've seen any Python, you know that we enter the program here and then we immediately jump into the main function. And here the only thing we actually do is we created an array from command line flags and we call the TOTP function with them as well as every key we get from the standard input. How this works exactly will become obvious when we try running the script. What's left is just two functions which implement the HOTP and TOTP. But first, what even is TOTP? I'm glad you asked. Again, TOTP stands for time-based one-time password, and as the name suggests, it's a password that changes based on the time it's being generated. But if you look at the implementation of a TOTP function, it just delegates the majority of its work to HOTP function. Right, so what's HOTP? Well, for starters, it stands for HMAC based one-time password. And what the hell does HMAC stand for? Stay with me here, Marine. HMAC is a hash-based message authentication code. And don't worry, even if we haven't reached the bottom of this barrel, this is as deep as we'll go. For our purposes, HMAC is a mechanism which uses a secret to create a signature from a message. This signature is irreversible, which means that you can't derive the key from it. Let me draw that for you. So me and you both know about the same key, and when I send you a message, I can use this key to create a signature from it. And when you receive this message, you can use the same key to calculate the signature. And if those two signatures are the same, you know that no one tampered with the message content while it was in transit. Okay, so we know what HMAC does. Now, how does HOTP work? The algorithm is clearly described in this RFC, but I think it's clearer if we just walk through the Python code and I explain the algorithm step by step there. So, HOTP requires two inputs. The first one is the secret key and the other one is a counter. Both parties, your phone and the server, must keep this value in sync, otherwise they will produce different results. I haven't noticed this first line in RFC, but all authenticator apps I tried use it, so let's stick with that. Let's just say that the secret string is ABCD and the counter is number 420. This first line I mentioned decodes the secret using base 32. Base 32 is essentially just a mechanism to allow transmitting binary sequences using text. I have a video about base 32's big brother base 64, which essentially just has more characters for encoding. You can watch this video here. With our inputs, the key variable here is a list of 2 bytes which look like this in hexadecimal format. The rest of this function is defined in the RFC, so don't worry if you don't exactly understand the rationales about all operations. Most of them are defined in a specific way, so that there are no unknowns and an implementation in no languages can produce the same result. If we didn't want our implementation to conform to those standards, this function could be as easy as calculating the hash from inputs and calculating its modulo of the digits variable. Anyways, the first line from the standard encodes the counter as a 64-bit big-endian integer. The next line produces an SAH1 HMAC with the secret as, well, secret and a counter as the message. In other, not exactly correct words, it signs the counter with the secret. The result is always a 20-byte long list. This list is too long to retype it from your phone to your computer every time you use it. So we need a way of truncating it into a smaller form. We do that by first making the 4 last significant bits from the last byte in this list. Here this is done using this not particularly readable syntax. We then interpret these 4 bits as an integer, and since there were only 4 bits, the highest possible number this offset can be is 15. Then we take this offset and use it to extract a chunk of 4 bytes from the HMAC. Remember, this HMAC is 20 bytes long and the largest offset is 15, so there is no danger of indexing the list past the end. Then we take these 4 bytes and use them to represent a single 32-bit integer from which we remove the most significant bit, so it basically becomes 31-bit. Then we take this number modulo 10 to the number of digits we want, which in our case is 6. Our implementation is a bit convoluted here, but achieves the same goal. We could achieve the same result like this. The implementation from the script though has the added benefit of padding the number with zeros if the number does not occupy all 6 digits. At the end of the day, it's just a matter of taste. So now that we know how to calculate an HOTP code, we can finally use it to implement TOTP. The only thing we really need to do is take the current Unix time divided by the time step and use this value instead of the counter for HOTP. Other parameters stay the same. By the way, this Unix timestamp is just a number of seconds that passed from an arbitrary point in history. All computers agree on what this point is, so we can rely on it to be the same. We still need our devices to regularly adjust their clocks so they don't drift too much. If your phone would drift for more than 30 seconds compared to the server, no code would work anymore. And now we're done. All there is left for us to do is try the script out. First, I'll echo out a string which will be our secret key in base 32 representation, and I'll redirect it to our script's standard input. When we run this, we get the code, but is it the correct one? I can also input the same code to a different OTP app and see if the number matches. I'll use an authenticator app on my phone to manually enter a new TOTP code. So under secret, I'll input the same secret as we had before. And when I click save, I should get the same secret as I do on the script. And as you can see, the numbers match. Now there is obviously much more to implementing a robust production-ready implementation of TOTP, but the concepts remain the same. The code for this example is also on my GitHub alongside other small examples which illustrate concepts like this. The link to this repository is in the description, and each of these examples in the repository also has their own video here on YouTube. Anyways, I hope you had a good time, and if you did, please consider liking this video and subscribing. Thanks for watching, and I hope to see you again. Bye!